Welcome to the demonstration corner. Today we're going to be talking about the MP series, the transient plane source method that's available on the three models of the MP series, and that's the MP1, the MPV, and the MP2. We'll be sharing the screen so we can see this more in depth, but this comparison of the transient plane source across the three models of the MP are available on the website as well, and there'll be a link in the description below. But let's go to the desktop and we'll talk a little bit about the transient plane source method specifications, what's different between that method on the three models of the measurement platform, and get into some demonstrations. Okay, so hopefully this is a little bit more legible. So the MP1 is our advanced model of measurement platform. It encompasses multiple methods, but we really want to focus on the transient plane source method, which follows ISO 22007-2 and the new -7. We recently did a demonstration on the -7 ISO standard and what that means in terms of the measurements. You can see the biggest differences are sort of across the board in the thermal conductivity range, the properties that each are measuring. The MP1 and the MPV both measure thermal conductivity, thermal diffusivity, specific heat, and thermal effusivity. The MP1 adds the ability to measure contact resistance and thermal resistance between two materials. It's a very unique capability. The measurement time is very specific to the thermal conductivity range as well as the flexibility of sample size. The minimum sample size you can see below, that is really caused by the ability to measure different time scales. There's a difference in accuracy, repeatability, the temperature range, the optional sensors that can be plugged into each measurement platform, and of course the testing modules that are available. So this is available. You can review this. So the MP1 is by itself. We have a common list of comparisons for the specifications in our mid-range MPV, which is our versatile MPV, and our portable MP2, which it does follow the exact same theory. It's an absolute method with no calibration. You don't need a drop of water between the sensor and the sample. It just has more narrow capability, but within that range of capability, it's a very interesting and versatile portable meter. So we invite you to learn more about that. So I'm going to move over to the MP1 and show for each measurement platform how you can measure with the transient plane source in a general way. So let's switch cameras. And we're going to go, so first we're going to just mention MP1. So this is our MP1. It's our advanced. It has a 4-channel controller that you can connect room temperature, sample holders, as well as the temperature platform, which is available in different ranges. All that can be controlled with the same controller. So this is like having 4 units side by side. We describe this as future-proofing your thermal conductivity needs. Our MPV, which just come back from a conference exposition for polymers in the UK. It has some of the same capabilities as the MP1, but of course a more narrow range for the mid-range market for measuring thermal conductivity. And then we have our MP2, which has all the same methods available, but just more narrow range in application. So if you have budget but need accuracy, that's the model you might look at. So we're going to show a sample setup using the transient plane source inside the temperature platform. Talk about that. And then on the MP1, we'll talk about a symmetric 2-sided setup on the bench so you have an understanding of both. So let's move over. Maybe we bring the camera over. So this is our temperature platform. The TPS TP stands for transient plane source temperature platform. The base temperature range of this is 0 to 300. And the thermal conductivity measurements are done at discrete steps of temperature. So it would go to each temperature, stabilize, make a measurement, or a number of measurements at that measurement, and then you can move on to the next temperature. Because the MP1 has multi-channel, you could actually add multiple temperature platforms side by side if you needed them. The optional range that you can extend this to is -45 to 300. Or -160 to 300 Celsius. So let's show the sample setup. So we're going to use our 6.4 millimeter diameter 4 contact points. They are slid under the sensor bar. I know the camera might not give you the best view of that, but there's a box. There's only one way to put it in. You would affix that with the knurled knobs. Make sure you have good contact. Electrically, the system confirms that. We'll lower the platform so that when we place we're going to set up symmetrically, so when we place our sample, it's sitting parallel to the sensor. A little bit more. So the floor can go up and down. The maximum sample size of samples inside the temperature platform are 40 millimeters diameter by up to 20 millimeters in height. And you can measure inside here symmetrically or asymmetric, so two-sided or single-sided. So once you have your 2 pieces of sample for symmetric configuration, you place your top on, you secure it, and this middle screw just secures the 2 samples together. This completes the cold environment around it, and this is our protection, which has a magnet switch inside of it, so that when it's off, the software, actually the temperature platform knows. So we put this back on, and that's a complete configuration. All the control of temperature can be done within the software. So we would typically move to the software and schedule a number of steps of temperature and move on. But we're going to come over here and we're going to show a symmetric setup for the MP1 using the sample holder. This one is room temperature configuration. You can upgrade this room temperature adapter to a 300 Celsius version so that you can use this as an oven. This would allow you to measure sample sizes much larger, up to 6-inch square and 2-inch thick. So I don't normally have to do this, but for demonstration, we'll show this is your 4 contacts. There's a insert location and a plate that we lower to create electrical contact. We just slide that in, and you can see there's a window. That window is when you know you have good contact, and then we just turn that, and that gives us our sensor setup. And we place it on the adapter bar, and that's how we account for change in height between sample sizes. So in this case, the demonstration that we're really describing is composites and polymers. This is Torlon polyimide. It has anisotropy because of extrusion. It's well organized. The anisotropy is so that we can use the anisotropic module. So for sample setup, we would place one on the bottom and lower the sensor till it sits relaxed, and then secure it. Place your sample on top, and we would introduce our little metal disc so we don't damage our sample. Lower our top bar and secure the sample. That's our configuration for room temperature, or if we had the upgraded adapter for 300, we would put this in an oven. We have ovens that communicate with the software so that you can run this all fully automated as well. So the temperature platform has many advantages over this because it's from the ground up designed to be fast and accurate and small and compact and controlled multi-channel. But when you need to be able to measure large samples, of course, it's nice to have this option. So this is the transient plane source sample holder for benchtop and sample setup for the temperature platform. So we're going to come over here. So the MPV has a very similar room temperature sample holder. So you would set your sensor up in a very similar way. And if we were measuring these Lexans, we could do that symmetrically by lowering the sample, the sensor rather, and affixing the sensor in this configuration. And if that was connected to the MPV, we would make measurements in a very similar way to the MP1. So you can make, inside this sample holder, for measuring polymers and composites, you can measure bulk properties, and you can measure anisotropic properties. It just depends on if your material is in fact directional due to process or added fillers, etc. So this is our additional sensor that's available on the MP series. This is our high temperature one that can go up to 200 Celsius. Its construction is absolute, so this is called the modified transient plane source, but the absolute version. What makes it absolute is that it follows the ideal theory of transient plane source, the transient plane source described in the 22007-2. So with this one, the construction is very simple. It's elegantly put together, but if you were to see, and we have another demonstration where we do break this apart and show what the construction of this is. So underneath the double spiral, which is stretched over a piece of foam, that foam underneath is a known material. So there's no calibration, no contact agent. Additionally, what this allows you to do is vary the test time and power. So because you can vary the test time and power, you're following the ideal theory for transient plane source, and you can make very good measurements across a wide range of conductivities. Additionally, you can use this same single-sided asymmetric or modified transient plane source sensor for measuring bulk properties, which is what we're going to set up. This is Pyroceram. This is a certified material for thermal diffusivity, Pyroceram 9606, but you can also measure one-dimensional. So the module for measuring along the height of a sample. You can also measure asymmetric slab, so that's for a conductive sheet. And you can measure anisotropic. So you can measure all of the different modules with this exact sensor. We're the only ones that do some of those single-sided configurations. And the performance difference is very small between our MTPS, the absolute version, and the symmetric version. So the two-sided is following the ideal theory, but this is the exact same approach. It's just with a configuration that we provide that has very similar performance and capabilities. So this is the cradle that comes with the MTPS sensor that allows you to just conveniently put it on your bench. It has silicone on the bottom that it doesn't move around. We can use a weight, or the cradle that comes with it can be used to just turn the sample down. So we're going to cover that raised circular area. We're going to introduce the same disc that we do on symmetric. The heat we introduce never hits the boundary, so that introduced disc does not affect the results. We'll just finger tight it, and then we'll move to the software and show you basic software setup. Okay, so here is we've already skipped to this tab, but this shows you the software auto identifies what's connected to it. So this is the serial number of the controller. Here is, we've only, the MPV has one channel, and right now we have the MTPS high temperature sensor connected. We've named the sample Pyroceram. These are the dimensions of the sample, and really those are the only inputs you required because of the iTPS, and I'll talk about that in a sec. Before we progress to the iTPS, we always check the resistance. We have already checked it once, but we can check it again. What that does is it verifies that the sensor is electrically complete, or a complete circuit, so that you don't have a short or a break. It tells you that your sensor is good. Temperature is automatic. The temperature of the room or the environment, excuse me, wherever you have that sample is recorded automatically. We can run the iTPS. Now what the iTPS does, the I stands for intelligent, it's our algorithm, which is more than just math. It's actually a proprietary approach to the measurement for determining the parameters. So because we're not calibrating one set of times, one set of powers, we don't need any calibration. Also, all of our MPV and MP1 have the ability to manually modify experiments, so you can have a deeper understanding. For the users that want, to be able to understand the manual approach, but automate the selection of parameters, the iTPS does that. And what it does is when you input the dimensions of your sample, it measures a really long test time to find the edge of the material. So when the heat hits the edge of the sample, there's a reflectance effect, and the software looks for that through that continuous measurement and calculation, and it determines a test time and power based off of that continuous measurement once it finds the boundaries. So because once it finds the boundaries, it knows the time of measurement to find that boundary. And that's a really intelligent approach to making the measurements and using the accurate parameters, but also with the understanding that you can do it manually. So let's run that. That does take a couple minutes. But while we're waiting for that, we'll switch and we'll show you the progress of this and continue the measurements and show you the data. We'll switch to the MP2, which is our portable version, and show you that experiment while this is running. So we're going to switch camera. So we're giving you a cross-section of the MP series. So this is our MP2, our portable measurement platform. This has transient hot wire, transient line source sensors that are available in the background. You can see them. Transient hot wire on the left, but we're here to really talk about the TPS. So this is again a single-sided sensor that has been stretched over foam, no calibration, it's absolute, so it follows the ideal theory. The thermal conductivity range of this device is noted on that specification comparison, so it's 0.03 to 5 watts per Kelvin, so it's designed for polymers and composites, pastes, and powders. So you place your sample on top. This one, you typically just use a weight just because of that narrow range. You can select a single measurement just by pushing the blue button. And what it does is it, excuse me, it records drift. So the drift is the environment of the temperature that the sensor and sample are in stable. It records that, so you want a nice random shape, and then it will record it will run the transient measurement and record the thermal conductivity on the device itself, which can be imported into the plugin software, and we can show you that as well. So here you see the transient of temperature rise versus time. Well, you might be able to see it. The camera angles might not be great. We'll lift that and bring it to the camera as soon as it's complete. We don't like to disturb it while it's actually running a measurement because that might move the sensor and generate erroneous data. I think in this case that's a 40-second measurement, sorry. There's 3 different test times available on the MP2, 10, 20, and 40 seconds, and that's dependent on the thermal conductivity and dimensions of your sample. So there's the thermal conductivity of Lexan. I'll just take it off and bring it up. You can see the thermal conductivity measured. So this one only generates thermal conductivity, where the other 2 MPs give you additional properties of diffusivity, thermal specific heat, and thermal effusivity. If you want to review several measurements, you can go to view data, and you can see here Lexan measured 7 times before that, and 8 is our last measurement. It's all around 0.22 at the same time and roughly the same room temperature. And we'll import that and show you what that data looks like as well. So there's a powder cell you can put on top of this for measuring powders with the TPS sensor. And then that's basic setup. This can be run off the wall voltage as well as 4 AA batteries, and it can also be run off your computer power. So it has basically you can get power from 3 different spots. So coming back to the desktop, we can see the continual measurement and the recommended time and power for the Pyroceram on the MPV. So this is the single-sided setup for Pyroceram in the recommended time, and of course here we can just go right into a schedule and make some measurements. So what you see, why that gap is there, is as that measurement is continuous making, that gap is the software calculating at different continuously calculating, and the measurement continues until it finds the edge of the material. And what's really interesting about that is if you're developing parameters manually, you would do one measurement of one time and adjust that time or power with another measurement. That's all fine, but you have to wait 5 or 10 minutes between each of those iterative measurements. This is one continuous measurement with calculations done continuously through the measurement, so that you don't have to stop and delay in between iterations, because it's one continuous measurement. So you're not getting a disturbance of one calculation range to another. So it's a continuous time measurement looking for the edge of the sample. So it saves a lot of time, but ultimately it gives you the recommended time and power. So here we can go to the schedule, and you can see our recommended time and power above, and we can add an experiment of, we'll do 5 tests with a 10-minute delay. That could be 5 minutes, I suppose. And we'll use that power, and we can start. And here you'll see five measurements at 4 seconds, with the first one being scheduled and the event log showing the sensor resistance. This is your data acquisition application, which controls the MPV for generating data. And then we have a separate application, so that schedule will continue to run. We have a separate application that lets you analyze data. So there's two applications that come with. First one is data acquisition, generates data and controls the scheduling, or if you have a temperature device, it would control all those hardware components. This is the thermal analysis, transient analysis application that lets you import that data and do measurements. So you can individually select an experiment and see the thermal conductivity and related properties, or select all of them. And then from here, you can generate a report. I'll show you what that looks like. And here you can see all of the same data and much more generations of graph and average data and percent RSD. So that's the MPV, but the MP1 works identically, except if you remember back to those comparison specifications, it does generate more data across different ranges of temperature and thermal conductivity, and a wide range of differences in capability. So let's import the MP2 data that we just run on Lexan. So we can select the device. There's our MP2, click OK. And here is the sensor used, the ID of that sample, timestamps, and the result for thermal conductivity. And you can click into each of these, and it gives you more information. If you want to see the heating graph, this is the columns of that, and the different information that can be mined from it, the power used. Also, you can delete, etc. So that's a summary of the data. So going back to the original PowerPoint showing the comparison, we just wanted to do a cross-section of the measurement platform across the measurement of polymers and composites, both for symmetric and asymmetric setup, as well as the TPS sensor, and how they're all similar but with just differences in ranges when it basically comes down to it. So there's an MPV or an MP that would be suitable for a wide range of budgets and applications, and that's what we have these for, because the thermal conductivity can cover a wide range of industries and applications. And we created these ranges so that users can select the ideal model and have room to upgrade if they in fact need to over time. Thank you for your time. We'll be doing more of these MP series comparison, where we take types of materials that are common and demonstrate them across all the MPs, the measurement platforms, to give a cross-sectional comparison so that users can see how they compare well within a small time frame. There are certainly plenty of demonstrations that have already been generated. You can see on our channel and playlist that are much more individual to the different MP for various types of materials, and I invite you to go look at those if you want to dig deeper, or contact us and we'll forward those playlists, because each MP has a playlist and we'll be doing more and more videos within those. So if you want to see, what can one model of the measurement platform do, you can dig in through the videos or contact us, and we'll set up a one-on-one demonstration. Thanks so much for your time, and look forward to demonstrating in the future.